Thank you so much, Emily, for that really wonderful introduction. Cecilia and I really want to thank the ARVO committee for this really prestigious honor. It is the greatest honor that two of us have ever received in our careers. And so it's a real pleasure to be here. Thank you also for braving the historic first of snow here at ARVO and coming to our lecture today. So I'm going to be talking about our journey with big data and machine learning, and I hope this story will be inspiring to some of the trainees here in the audience. These are my financial disclosures.
And my only disclosure is that I'm married to Aaron.
And the other disclosure is that AI was definitely used to help generate these slides. So we want to walk you through our journey from when we were first getting started in clinical research. And if we rewind the clock all the way back to the era of paper charts, things were a lot more painful in terms of trying to get data to do research. I started my journey at WashU in St. Louis, as you heard. I was a third-year medical student, and I didn't think I had a chance to become an ophthalmologist because I hadn't done so well on my board exams. And so I took a year off to do research, and I did that with Mylan Brantley and Russ Van Gelder. And the very first paper I ever published was studying the pharmacogenetic effect of CFH, the Y402H mutation, in the treatment and need for anti-VEGF injections in AMD. I also helped develop the computational methods to scale and study metagenomics in Russ Van Gelder's lab, and helped develop the pipelines for informatics. And these two projects really gave me the foundation for trying to understand how to do clinical research well, and the computational experience that really played a pivotal role throughout my career.
So my journey started at Emory University, and this was an era where careful attention was made to individual patients and imaging characteristics, and that's what really led to discovery and science. I'm especially grateful for Valerie Views and Nancy Newman, who took me as a medical student and really taught me how to design a study and execute an RCT. We published a paper on the effect of vision restoration therapy in treating NAI1 patients. During residency, I really want to thank Steve Ye, because he was not only a mentor in uveitis, but really taught me how to think and leverage multimodal retinal imaging and use that as a source of biomarkers and also source of insights into mechanistic pathways of difficult and challenging diseases. Actually, my first ARVO presentation was in fundus autofluorescence findings in white dot syndromes. And the subsequent year, I came back and presented on multimodal retinal imaging characteristics of unilateral acute idiopathic maculopathy. As Aaron mentioned, these foundational years were really critical for me because it really taught me how to think about a study, not was because we could answer all the questions, but really taught me what was important to measure enough in a larger, more complex data sets when they emerge in future. So both Aaron and I lived in this transition of manual research era to digital records era. We actually were trained as medical students to take good notes in our paper charts, but during ophthalmology residency, we firsthand witnessed the transition from our paper charts to various sources of EPIC in different hospitals. And that really changed our paradigm of how we approach our research and how we do research. And it was no longer the case that our questions were limited by access to patients or how many charts we could actually abstract out of our storage rooms and transfer that information to a spreadsheet. It was really limited to our capacity to mine our data and deal with the complexity and making meaningful connections along different data sets. It opened the door to discovery at scale, but we also learned that we need new tools and new approaches to overcome those challenges of big data. So we couldn't do this talk without thanking Gary Holland, and Emily mentioned briefly. And yes, we met at this UCLA AUPO Introduction to Clinical Research course, and many thanks to NEI for funding this course. And Aaron and I were both sent from our residency programs. And it was actually the first year that I participated at ARVO. And it was actually, that was the reason why Aaron was able to get my phone number, because he said, I can show ARVO around. So we met, and actually the ARVO in 2011 was the first time we had an official date. And I can tell you and confirm firsthand that networking at ARVO can be very productive because within 1 year, we were married and we are here.
So as Cecilia mentioned, we were kind of in this, witnessing firsthand this transition from paper charts to electronic health records. And one of the things that we realized was that all of a sudden, that painstaking manual process of taking information from a paper chart and putting it into Excel really was going to change fundamentally. But while we were here in the US, we realized that when we got to the UK and the next step of our training pathway, we were at Moorfields doing our medical retina fellowship. And there we met Adnan Tufail and Kathy Egan, and our co-fellow at the time was Pierce Keane. And the UK had actually been well ahead of the United States in terms of the digitization of medical records. And they had collected many, many different EHR data sets across the different trusts and brought them together into these very large registries. And what we were able to do very quickly is start to do analyses at scale. And we kept hearing over and over that the old way of doing statistics or opening data sets in Excel wouldn't work anymore because it would crash the programs. So taking advantage of this, we were able to build these beautiful visualizations that showed patients' visual acuity trajectories as they were being treated on anti-VEGF. And we also were able to look at really important questions at the time, such as what would happen to patients who were being treated on ranibizumab and they were switched to aflibercept. What would happen to their visual acuity? Would it sustain, that gain sustain over time? Because of all the data that we had there, we went on to publish many, many papers in collaboration with the UK group. And we studied things like what would happen to the rate of progression or change in diabetic retinopathy over time. We also showed for the first time that the risk of increased additional intravitreal injections led to a higher rate of posterior capsular rupture during cataract surgery. And we were also lucky enough to participate in some of the very first head-to-head AI studies that looked at the effectiveness of these screening programs when they were switched to an automated system.
So under the mentorship of Russ Van Gelder, we arrived at University of Washington, and this is where we really crystallized our concept of computational ophthalmology. We were living in this new era of data and data environment. And computational ophthalmology for us, it really means a shift from qualitative analysis or interpretation to quantitative discovery. So we are leveraging all sorts of data sets, big data sets, to gain insight not only into visual systems and eye diseases, but really to understand overall systemic health and aging. Actually, when we were at University of Washington, we really did many different studies of different topics, such as what is the driving distance rate difference between optometry offices and ophthalmology offices? Do they actually make a difference in which you get cataract surgery or not? One of the studies that we both got involved with Russ was really in the bioinformatics and molecular sequencing And we found that molecular signatures can be very predictive of clinical outcomes of vision-threatening diseases such as endophthalmitis. IRIS registry, as you know, it is the largest clinical registry database in the world. And this really represents a unique opportunity that we were lucky to be involved in, and we were able to answer many questions that were simply not possible before. This was under leadership of Mike Chang, Flora alum, later by Emily Chu. And we asked questions such as, if you undergo cataract surgery, one eye at a time versus both eyes on the same day, is there an increased rate of endophthalmitis? And we found that that was not true. We asked, is the refractive outcome different then? Because those are two reasons why we were told you should not be doing both eyes surgery at the same time. And we found out, yes, there is a difference, but it's really not clinically meaningful because we found a difference of 3 letters, which is not even enough to be one-line difference. Questions like, what is the healthcare disparity among pediatric population that have strabismus, JRA, and then also what about surgical interventions for people who have Fuchs dystrophy? If you have a specific race or specific insurance, do you get offered PKP as your first therapy versus DMIC and DSEC? While we are involved in this big data using ARIS to get really eye disease-related questions, we got exposed and we got introduced to colleagues in non-ophthalmology departments. I want to thank Eric Larson and Paul Crane at University of Washington because they had access to this beautiful population-based comprehensive longitudinal data sets. And this is where we learned that those data sets are really critical. You need longitudinal comprehensive data sets so that you can ask questions beyond the eye. Can we use the eye data to predict who's going to develop dementia and systemic complications? So one of the examples were we found that AMD and diabetic retinopathy are associated with about 50 to 60% higher risk of developing Alzheimer's disease, which is really remarkable because that is as high as you having an ApoE4 allele, a genetic risk factor for Alzheimer's disease. We also found that cataract surgery is associated about 30% reduced risk of developing dementia and Alzheimer's. And all these findings were solidified when the most recent Lancet Commission report reported vision loss as one of the newly established modifiable risk factor for dementia. So by integrating this longitudinal data and also collaboration of cross-disciplinary expertise, so we are really moving beyond ophthalmology field, we really got to involve many different study questions, and a lot of you here have been part of our journey. So as big data studies became really our focus, we realized that no longer statistical p-values were really meant much in big data. So what we became focused is to really visualize our raw data, because when we are able to visualize and are able to identify specific patterns, trajectories, or distributions among comparator groups, it usually meant that they are clinically significant and biologically meaningful in most of the cases. So this is what we have been doing and really enabling next generation of discovery by visualizing the large data sets that were just not possible with just p-values alone.
So the other major inflection point in our careers came as not only the electronic health records were put into these enterprise data warehouses and made available for research, but also imaging and testing that we were doing routinely in our clinics, things like OCT and color fundus photos and visual fields, were being collated and collected in a centralized location, and we could start to harness that. And at the time, in the early days, if you just had a whole bunch of these, there was really not that much you could do. It wasn't until the advent of deep learning and computer vision that suddenly the world of possibilities really exploded. I want to share with you a couple examples that I think are really kind of compelling. This is a video of us doing semantic segmentation, where we are segmenting the upper eyelid and measuring MRD1 at a sub-millisecond resolution. And all it took to do this is just an iPhone with the slow-mo feature. The state-of-the-art before this was taping a magnetic coil to the upper eyelid and telling patients, pretend like it's not there and blink normally. We also were able to automate tonometry readings by strapping, again, an iPhone to a slit lamp and taking videos. And if you did that with fixed force tonometry, you could measure things like the ocular pulse amplitude. And this was a project that was done in collaboration with Joanne Wen. One of the things that we were really excited about was this paper that we published in JAMA Network Open. This was in collaboration with the MacTel Consortium. We showed for the first time that you could take OCTs and predict what the retinal sensitivity was at that particular location for every A-scan location in a macular OCT volume. And by doing that, you could create these high-resolution maps of what you would expect the perimetry values to be at every given position in the macula. This concept is now sort of evolving into what people are calling functional OCT today. But this paper was really the first in 2017-18 to kind of showcase this. We also disentangled the structure-function relationship in glaucoma. So by training models to study the different defects that were present on the optic nerve, we could try and disentangle each position of the retinal neurofiber layer emanating from the disc, and which positions on the 24-2 were most reliant on those positions. And finally, this is our unpublished work. This is a YouTube video of somebody with an adduction defect and end-gaze nystagmus. And we are automatically extracting and measuring the excursion and quantifying those in millimeters and able to back out things like the cycle frequency of nystagmus, all in a fully autonomous fashion. So this body of work really set a foundation in the field for how we can use deep learning to do many different things. Some of the papers that we've published were really the first to demonstrate that you could use deep learning to analyze OCTs for various different tasks. And we were very excited to do this not just in the field of retina, but really across the field of ophthalmology, both in glaucoma and oculoplastics, as you saw. And we've collaborated outside of ophthalmology to do some of this work in neuroradiology as well.
So as the field matured, we recognized a critical need for a diverse, multimodal, and AI-ready data set to train really large, sophisticated models. And the Bridge to AI program was really in line with what we were thinking. We really needed a data set that was not as biased, so not healthy patient bias or sick patient bias, such as EHR-based data sets. And this was really about building an AI data ecosystem, much more beyond than just recruiting participants and getting data. We are very lucky to be one of the 4 funded programs in which our goal was to generate multimodal, AI-ready, diverse, ethically sourced data sets to enable the study of both pathogenesis and salutogenesis in type 2 diabetes. And so we are very much in a trench of really getting our goal. And we realized that to build this data ecosystem, we wanted to be very careful and intentional from the beginning in how to design the study. We are recruiting a total of 4,000 participants, but we are making it balanced so that demographic characteristics and also the disease spectrum is balanced, starting from no disease state to pre-diabetic, medication-controlled, and insulin-controlled diabetics. And we go from head to toe. So we go from cognition, depression, social determinants of health survey, and we go to visual function, retinal imaging. I'm sure many of you will be very pleased that each participant undergoes 44 different scanning patterns of retinal imaging. And this was really our attempt to enable a data set that could be either benchmarked or also used for harmonization purposes, as we recognize that this is a big challenge in our field due to lack of standardization and harmonization. Then we go to 12 lead EKGs, and we go body measurement, blood and urine testing, and all the way to the bottom of sole, where we check for the neuropathy level. They get discharged with 10-day data collection of continuous glucose monitoring, physical activity tracking, and also environmental sensor measurements, in which they take 22 different environmental sensor measurements along with the light spectrometer meeting every 5 seconds. We are very excited that at the end of the study, we'll be able to get whole genome sequencing and then proteomics and metabolomics data available as well. We are actually ahead of our schedule. We have less than 125 more participants to go, which is a great testament to the hard work and really amazing work that has been done, especially for the 3 data collection sites at the University of Alabama at Birmingham, UCSD, and University of Washington. We wanted this data ecosystem to be patient or participant-centered, so we've started participant or patient community engagement from the beginning. We're very pleased that even though we have this incredibly arduous data collection pipeline where they spend up to 5 hours with us in the data visit, over 98% were really pleased and satisfied, and they would recommend this study to other friends. We held our first open house where we invited all the past participants last year, in which we shared our updates, progress, to maintain this partnership and build trust among our public and our research participants. One of the greatest success measures that we want to get is really to share data and make sure that this data set is available for all our community. We worked hard with bioethicists. Sometimes the arguments were not pleasant, but we work hard with bioethicists, researchers, and community partners to make sure that we find this balance between protecting the data privacy of our participants, but at the same time making our data set as accessible as possible. So we consider this data sharing paradigm as Swiss cheese model, in which we recognize that no single method is good enough to guarantee that we can protect the data. But by combining multiple methods, we are doing our best to protect the privacy of our data set. And because of these measurements, or because of some of the methods, were creating specific license that prohibits any attempts to re-identify participants, and also coming up with watermarking system in which every single downloaded data set is slightly different so that it becomes identifiable if this becomes leaked. And we are very honored and really excited that over 950 research organizations worldwide have been able to download this data set, and many of research that were presented at this year ARVO had AI-ready data set as well. We do have a different type of data set, which is controlled access, and that goes through the usual mechanism that involves DUAs and data access committee. We are excited and remain committed to increase the awareness and also teaching and developing the next generation researchers so that they can leverage our data set as much as they can. We held the AI course on last Saturday, and we are having a Mikai Data Challenge this year in collaboration with Jay Shiri at University of Colorado. And we hope that many of you can participate in this data challenge where we are looking into domain adaptation between different imaging. All this work would not be possible without the hard work and really the commitment from researchers, and many of them are actually here present. I want to thank especially Cynthia Osley from UAB at Birmingham, Linda and Sally from UCSD, and then Mark Christopher as well, and also Bhavesh Patel from CAMI and Michelle River.
So you've sort of heard our journey up until this point. We were, as clinician scientists looking at the field and trying to be at the forefront, we were trying to fill different gaps that we saw along the way. In the early phase, we were trying to show the world the power of deep learning and AI. And in the second phase, we realized that we needed data sets that people could use, data sets that were robust and that could lead to models that could actually be used in the real world. I think we are in a very exciting time now where we can start to translate these concepts and technologies into the clinic, and that's something that we really want to be at the forefront of at WashU. I want to highlight two projects that we were a part of, and this was just published online at Nature Biomedical Engineering 2 weeks ago. This was a collaboration that we did with Sheng Wang's lab at University of Washington and Zux Liu, who is the first author. And here we were trying to train a foundation model, kind of like RetFound that a lot of you are familiar with, but to sort of take the next step in that journey. OCTs, one of its great strengths is that it's three-dimensional. And that there's volumetric information that is hard even for clinicians to understand. And so we wanted to be able to train a foundation model that could exploit that information. And that was the concept behind this model that we call OCT Cube. The other innovation in this paper was the idea of being able to cross-train and bring in multimodal imaging at the same time. So could we embed both the IR reflectance and fundus autofluorescence images along with the OCT from a single encounter and have models be able to exploit all that information to do some sort of downstream task? We showed in the paper that if you look at different things like predicting somebody's hemoglobin A1C or whether they had AMD or not, this approach actually did very, very well. And really across the entire spectrum of different AI tasks, we showed that this model that we call OCT Cube could really take the next step there. One very important finding that was buried in the paper, and if you do read it, please read it to the very end, is this concept of using AI to make clinical trials better. I think we all know that there's a fundamental gap in the way that we do clinical trials today, in that they take too long or they require too many patients. And if we can use AI in a way to make these trials more powerful, we might be able to move faster in the field. The other paper that I want to highlight is this work by Nayun Kim. Nayun is our first MD PhD student that we had in the lab, and she just defended successfully about 2 weeks ago. The central work in her thesis was this idea of solving the reproducibility crisis that we're in right now, where it's very hard to reproduce a lot of the major findings in some of the journals. In addition, there's a growing divide that we see as data science becomes more advanced and the techniques become harder to understand versus the clinicians and their domain gap that we see. And so we wanted to see if large language models could be used as a way to bridge these gaps. So what Nayun did was she developed this framework called LATCH. LATCH stands for LM-Assisted Testing of Clinical Hypotheses. And the way it works is that you as a user would just type in a sentence of what you wanted to study. You would give it in sort of a natural way as if you were telling your student to go and do this analysis. And what Latch would then do is go through a multi-agentic framework to pull out the relevant information from a data set and then build a cohort and finally run the statistical analysis in a fully autonomous fashion. A really key point here is that the large language models is not getting access to the data itself. It's only getting access to the schema, the information of what each of these variables are. And that is enough for the model to then do the transforms to get the data ready for analysis. At the end of this, you would get a report. This is an analytic report that is automatically generated. It shows you exactly which data set was used, what years of that data set was used for the analysis, and then gives you the schema mapping that occurred behind the scenes of how it said, this word in your original query is mapped to this variable in the data set. It will then compile, give you the exact SQL code so that you can double check what the framework was using. And finally, also give you the R code as well as the statistical analysis with the odds ratio and the 95% confidence intervals. We showed in our work that we could reproduce many of the papers throughout the medical literature. So we really scoured as many papers as we could, and for every paper we looked at the point estimate as well as the 95% confidence intervals, and we see how well we could reproduce those findings. Even for more complex models like Cox regression survival type analyses, we're able to reproduce the hazard ratios, as well as point prevalence estimate type analyses. The really amazing thing about this framework is that we could reproduce 200 hypotheses in 20 minutes. And it's really sort of the next level of acceleration that we're going to see in biomedical science. So Cecilia and I really wanted to share with you the evolution of ophthalmology that we were able to witness sort of firsthand and in some cases drive. We started all the way from pulling charts ourselves from the big libraries of paper charts to this era that we now call big data, where huge data sets are now collated and available for research, to ecosystems where now we have agentic AI frameworks that are going to drive the next level of precision health in the future.
People say that it's all about who you meet in the right time, right place, and right data sets. And we are the living proof of that. It's because we have met so many mentors, so many collaborators, colleagues, and friends who have really supported us and really participated in our journey. Our career has been all about serendipitous path, and we want to be really we want to take this time to show our gratitude for all your support and hard work that have really helped us shape our career. I know when we say the productivity, between our collaboration, I tend to bring clinical epidemiology and big data perspective, while Aaron brings AI and technical expertise to our collaboration. But I know we have been more productive at a different level as well. This is EB, and if you have been on a Zoom meetings with us, you probably have seen her running around in the background, but she's also trying to learn. And she has promised me that any research that I don't finish, she will be able to continue that for me. We want to thank all our lab members now across the states, and also our collaborators again across the globe, and generous funding sources, and also the ARVO as well, because ARVO has provided us our scientific home and our place to communicate, to meet our collaborators, and really grow and do science. We also want to thank the award committee members. We did hear that the reason why we got the combined award was because they couldn't figure out who was doing what. But we really want to thank everyone for being here and really grateful for your support. Thank you.